Hi, my name is Jim Dowling. Welcome to this online event on understanding performance and availability of feature stores. I work for a company called Hopsworks, and Hopsworks itself is a platform for machine learning collaboration that powers the leading Python-centric enterprise feature store. But today we're going to talk about performance and availability of feature stores, and let's start by defining what a feature store itself is. What is a feature store for machine learning? And we'll start by defining what the situation may look like for those companies or organizations that don't have a feature store. So we can see here on the left we have some enterprise data and a data engineer responsible for that data. You're possibly using that data for business intelligence. And then the company or organization recruits a data scientist or a bunch of data scientists, and they decide to keep them away from the enterprise data by this silo. So you can see our data scientist is siloed. So when the data scientist wants to train models, they have to ask the data engineer for a dump of data. And when the data scientist trains a model, she gives it to the machine learning engineer or an operations person whose job is to put that model in production. And when the model is being put into production, it needs to be connected back to the enterprise data because the models need data to make predictions. So you can guess that this is not a very effective way of collaborating between the different teams and enabling data to flow easily between the different systems. The feature store is a platform that enables this collaboration and this smooth data flow between the enterprise data and the models that are serving in production. So it's a platform that will enable you to turn your enterprise data into features and then use those features for training models, but also for serving operational models. And it's a collaborative platform where the different personas, our data engineer, our ML engineer, and our data scientist, can all work together. So that's what a feature store is. And when we talk about performance and availability of feature stores, what do we mean? So many of you may think that a feature store is kind of like a database. So availability of a feature store at a database means pretty much the same thing. It means when I want to write to the feature store, will it be available? When I want to read from the feature store, will it be available? What's the throughput of the feature store going to be when I want to write to it, when I want to read from it? What will the latency of the feature store be? How long will it take for the feature store to respond with my features when I ask for them? And then finally, this is where the feature store differs from traditional databases, feature freshness. So if I'm going to make a prediction with a piece of data we call a feature is really just this compressed signal that we use to train our models, our machine learning models, but also to make predictions with. So we have pre-computed features that the feature store will make available to the applications. But if those pre-computed features are old, if they're not fresh, they're not going to be potentially useful to the prediction problem you're trying to solve. You'll know that yourself based on the prediction problem you're solving, but feature freshness is a property of the performance of feature stores. And it's something that maybe people from a database background will find novel. So, why should you care about performance and availability? They're very high-level topics. You just want to get a POC done. You want to show that the feature store can add value. But maybe if you think a bit more long-term, it can impact your business in many different ways. So I'm going to tell a few stories, war stories if you will, that I've encountered along my journey in working with feature stores. So if we start with availability, I know a large retailer who were using an embedded in-memory database to serve features to applications, and it was using a recommender system. So this recommender system stopped working on Black Friday because the system became overloaded, the database crashed, the database was not highly available, and that meant that the recommendations coming out on Black Friday were not as good as they could have been, and this led to revenue loss. What about throughput? Why should you care about throughput? Well, we work with a bank who've been building fraud prediction models, and for the first few use cases, this worked great. We took some historical financial data that was transferred. We looked at the batch data that was coming in daily, and this worked great on Python and Pandas. But then when we tried to introduce a new use case for fraud based on micropayments, so mobile payments between individuals, the order of magnitude of data increased. The data increased by an order of magnitude in size, if you will. And that basically meant that we couldn't process the data in the time we had available with Python and Pandas, and we had to switch to a more scalable feature engineering platform, and this time we chose PySpark. Freshness. So we also work with a company doing network intrusion detection, and they know for this particular problem they're replacing old rule-based approaches with pattern-based approaches. So machine learning identifies patterns better than the existing static rule-based approaches. But if the data that you're making your predictions is old, well, then it's not going to be a very effective network intrusion detection system. So Spark streaming is one way to reduce the age of your features, to increase their freshness or improve their freshness. But Flink is another streaming engine which is actually even lower latency and gives you even fresher features than Flink. So they were able to reduce the age of their features from 10 seconds down to 2 seconds. And this improves the intrusion detection rate. And most importantly, it creates a great leverage for their platform to position it as the leading platform in their space with this competitive advantage of the freshest features. And finally, in latency, so how long does it take you to retrieve your features? And you may think, okay, if I have an online credit card system that's doing fraud, it's got a budget of 5 milliseconds to get the features from the feature store, and that will be a standard use case for latency. But there are also other interesting, maybe non-typical use cases where latency are very important. So in the recent area of real-time recommendation services, so retrieval and ranking infrastructures, we worked with Spotify, who were benchmarking our database RonDB, in particular for doing lookups of 250 candidates that were retrieved from an embedding store, and then we had to score those 250 candidates. But in order to score them, we had to retrieve all the features from the feature store. So 250 primary key lookups in the feature store had to be all retrieved with a P99 latency of less than 30 milliseconds. So that data is publicly available if you want to read up on it. So why should you care about it? So these are some of the war stories we've seen, but really if you're going to move your machine learning models from experimentation to production, then you'll need to consider these issues of performance availability, because you want to plan into the future. If your system is going to be successful, if your models are going to be successful, generate revenue, reduce costs, then your data volumes will grow, your uptime requirements will increase, and potentially you'll have new use cases that have feature freshness or low latency requirements. So if you're considering performance and availability for your feature store, there's really only 3 different parts of the feature store, or interfaces we could say, to the feature store you need to care about. And then there's the feature store itself. So firstly, we write to the feature store with what we call feature pipelines. So we have to compute features in some way. We need some compute to do it. It could be a data warehouse that's computing features with aggregations. It could be a Python program. It could be a Spark program or a Flink program. They're going to write the features of feature store, or maybe mount them as pre-made features if you're using an external data warehouse. But then we need clients who are going to use those features. So for the data scientists who want to train models, they'll use the training and batch data API. So this is the API that will give you batches of data to train models with, but also batches of data for scoring for your batch models. And then for the online models or operational models, we have this inference API. So we're able to retrieve features to score models with. So pre-computed features that are stored in the feature store can be retrieved with very low latency from the feature store at runtime. The feature store itself also needs to be available or highly available if it's going to always be available for reading and writing. So let's go dig into some of these properties that we've already introduced, the 4 properties: latency, throughput, availability, and freshness of features, for each of these different interfaces and the feature store itself. So starting with feature pipeline, feature freshness might mean that you start writing your first feature pipelines in Pandas and Python, because many of your data scientists are familiar with them. Your data engineers are also comfortable with Python. So you write some features in Python and you're happy, and you run them on a schedule. So you're going to update them every hour and you're happy with that. But then a new use case comes along where you need fresher features, maybe 15 minutes. And batch scheduling still kind of works. You might get some late data, but it might work quite well. But once you reduce the time required, to make your features available to the inference applications, then you might need to switch to streaming engines. So Spark streaming, Flink streaming. Throughput. So again, if you start with Python and Pandas, you might say, well, this is working quite well, but I need to be able to seamlessly change from using Python and Pandas to a more scalable technology that can write more data per unit time. So technologies such as Spark, PySpark, which is quite compatible with any code you've written in Pandas. So if you've written features in Pandas and you want to translate that or port that code to run on PySpark, generally it's quite straightforward. Both of them build around the concept of a data frame, and some tweaks to your code, you might be able to then make it scale out quite nicely to write higher throughput features to the feature store. Also, data warehouses have great capabilities in terms of performing aggregations on huge volumes of data, and then you can make that data available in the feature store. In Hopsworks, you make it available by mounting the external tables from your data warehouse directly in the feature store. If you're doing inference on the feature store, I mentioned Spotify were benchmarking our database. They benchmark many millions of operations per second. You typically won't get that kind of performance on a single virtual machine. You'll need to make it distributed. So throughput in this case means being able to scale from a single virtual machine to many virtual machines or nodes in your database cluster to provide the available number of requests per second that your online applications require. And then finally, when you're creating training data or when you're creating batch data for scoring, you may have requirements on making that data available to your users in a relatively brief amount of time. So your data scientists are not sitting around for hours waiting for their training data to be created or their batch data to be available for scoring. The feature store itself has the property of availability. So our pipelines for writing and reading, they run from, they're really, I guess it's the external applications that determine the cadence of the writing, and also the external applications related to retrieving the features. But the feature store itself, we can talk about how highly available it is. If it's run on a single virtual machine, on a single database, well, if that crashes, it's no longer available. So high availability generally means replicated services. So underlying our feature store, we have a database around DB that can be replicated. But we also have, and that's our online feature store, but we also have an offline feature store. And in our case, the offline feature store are hoodie tables, and they're stored in S3 in the cloud, or on any object store, so GCS on Google Cloud, and Azure Data Lake on AWS, and our version of HDFS, HopsFS if you're on premise. So we have high availability for the offline store there as well. But typically you may have different requirements, so higher availability on your online store than your offline store, because it's driving operational applications. And then finally, latency. So you care primarily about latency for the inference data, so retrieving the pre-computed features to your operational applications or your operational models. So let's look at a few rules of thumb for when if you're starting out small, which is a really good way to start. So start with Python and Pandas because you're familiar with them, and it's a great way to just create some features, train some models, and serve those models and applications in Python. And if you're to move from Python on, at what point do you need to consider performance and how should you go about it? So let's start with looking at the feature pipelines where we're writing to the feature store. So if you're scheduling a Spark application or a Python application, they can run pretty much up to a cadence of 15 minutes. But when the cadence gets lower than that, depending on how long they take to run, to write each batch, and depending on how long it takes to start them up. So a Spark application, for example, takes longer to schedule than a Python application typically. But a rule of thumb is if it's going to be less than 15 minutes old between each write, or a 15-minute gap between each write, you might want to consider moving to a streaming application. The streaming application will be run 24/7, and it will continually write to the feature store. And you will get much fresher features. They'll be seconds of age at the most compared to 15 minutes. Your features can be up to 15 minutes old if you have 15-minute cadence on your feature pipelines. Now, if you're writing feature pipelines in Pandas and Python, and you tend to write maybe tens or hundreds of gigabytes at a time, you probably should think about moving over to a different technology. Now that could be Flink or Spark or a data warehouse, but Python has its limits. Often it's memory, and then of course we have the global interpreter lock, which means a lot of operations are single threaded in Python. Now throughput, if you're creating training data and batch data for scoring, and you're getting that data as pandas data frames, again it will work fine up to the available memory in your machine, but you could say, well, I've got a machine with a terabyte, but it takes a long time to read up a terabyte of data into memory on a single machine. If you have 10 machines, you can parallelize that and make it 10 times faster. And the same principle is available for training data. We can spread our training data across many files and many machines, and it can be created 10 times faster if we use 10 workers to create them. So training data up to gigabytes, pandas data frames are fine, but then moving into tens or hundreds of gigabytes, you might want to make your training data and also even batch scoring data available as files. So it could be TF record files or CSV files. High availability. So this really depends on your application requirements. If you start with batch, you may not have high availability requirements on the feature store to begin with. If you have an operational application, a fraud application that needs a feature store to be available to score particular transactions to say if they're suspected of fraud or not, well, you need this thing to be up. So our particular database RonDB is used in many telecom applications in scenarios where it has up to 7 nines of availability. So that means a few seconds of downtime per year. So really start with saying how much will downtime cost you. If it's going to be expensive, get a feature store which will provide an SLA for you that meets your required needs of service. And latency finally. So what's the highest latency you can tolerate for retrieving features? This depends on your service. So if you're doing fraud scoring for credit card transactions, you might have a very tight latency budget. So it might be 5 milliseconds or 7 milliseconds. If you're just maybe have some entertainment application which is going to show people a different version of their face or an interpretation of their face or something like that, then obviously latency won't be as important. You may also need to think for your inference what kind of throughput you need to support. So if you're going to have a successful application that's generating a lot of value for the business, maybe it's going to require higher throughput on your feature store. So then you're at the question of, well, will my feature store scale out? If you have a feature store running with a single MySQL server behind it, you're going to reach the limits of throughput pretty quickly with a few thousand transactions per second. But then, you need a system that will scale out. And again, our database RonDB does that for you. So the question is really at this point is, if you're going to pick a feature store, what do you need to care about in terms of performance availability? Now, from day one, many of these concerns may not be your primary decision points in terms of selecting a feature store, but really what you need to think about is, what would happen if my model were successful? What would happen in terms of throughput I would need to have, in terms of freshness of the features, if new use cases come on board and I need lower latency? What if I need to make the thing highly available? Will I be able to do it? Will I need to rewrite all my feature pipelines and my feature reading code because I need to switch off this system which isn't giving me these properties? And you want your feature store to help you seamlessly go from small scale Python pandas to larger scale PySpark, Flink, and data warehousing. So that really is part of your journey, and that's most businesses who are adopting AI. They'll start out and they'll manage their data. So if you don't have any data under management, you're really, if we think of Maslow's hierarchy of needs, the bottom of the hierarchy of needs is you need to manage your data and have it structured. So typically this means a data warehouse or a data lake. And if you don't have your data in a manner that you can do simple business intelligence on it, so query the data for historical patterns, it's unlikely you'll make that leap to do predictive models in AI. So typically you'll start out by doing some laptop ML, where you'll take some data and see if you can train a model and predict something with the model, and if that can help the underlying business, well then this is something you might think, well, this is something we'd like to generate business value from. We'd like to build a prediction service. So the prediction service is going to be more than just a model. It's going to be the pipelines that create the new features that are going to be used to make predictions. So we're going to have batches of data arriving on a schedule every hour, every day. We're going to use the model to make predictions with those batches of data, and we'll make reports out of there. So this is a lot of infrastructure around just the model. And you may see that this generates a lot of business value, but you want to build, and we could use an example of, I mentioned Spotify earlier, but imagine we have a video service that gives you predictions, right? So it says, I predict or recommend this particular video for you. And it's using it based on yesterday's data. So yes, it's doing real-time recommendations for you, but the data it uses the videos you looked at yesterday, which you may think is nice, but then along come TikTok, and they base it on the videos you looked at 5 seconds ago. And then you get a really interactive recommendation system that the users feel understands their needs, and it's very hard then for the other video service to compete because they don't have that missing secret sauce. So Hopsworks is a complete machine learning platform. It consists of, as we saw already, the feature store for machine learning, but it's a collaborative platform where you can bring teams together, you can bring the data together from the enterprise, because a lot of the data used from AI will not just be in your data warehouse or your data lake. Sometimes it's going to be in other data sources. You may have Elasticsearch or MongoDB, you may have data that's just lying on external systems that you really want to bring in periodically to make predictions with. It gives us performance that we talked about already, and then it's available on any platform. So you can install Hopsworks on premise. It's available as a managed service on AWS, Azure, and GCP today. So in terms of teams, what Hopsworks enables you to do is bring together the personas we saw already. So data scientists, data engineers, ML engineers, but also even business analysts, people who understand the data. Because if you're going to build prediction models, often they're the domain experts who will be able to help you refine your models and make better predictions. And the abstraction that we provide to organize your teams of these different personas is what we call projects. So a Hopsworks cluster can support many different projects. You can have them for organizing around a classical CI/CD pipeline where you have development, you have staging, and then you have production, or you can have projects that are related to different teams or organizations. So you may have this particular business unit has a project with its data, and a different business unit has different projects related to its data. And the project itself is a sandbox. It keeps the data inside it private to the people who are members of the project, and it enables them to collaborate to provide the service or models that that particular project has responsibility for. So the projects, if you were to dig a little bit deeper, they have some abstractions. The feature groups is where we store reusable features, which can be available offline, they can be available online, they can come from external data warehouses. We read the data from the feature stores. We reuse the features across many different models by something called feature views. So a feature view is a logical representation of features from different feature groups, and enables you to say, okay, this is the features I'm going to use to train my model with. I need some training data for it. And you go to the feature view and you get your training data. And then your model that's running online goes to the feature store and says, I need the features, the pre-computed features for this model that I trained with that training data. And they have the same set of features. So the same logical or view over the features in the feature groups. Now, if your projects were just sandboxes, it mightn't be as useful as you would like a platform to be, because you want often to share not just features across models, but even data sets between teams. So maybe training data sets, maybe features, So Hopsworks enables this controlled sharing of data between these projects. So you can explicitly say, I would like to share this data read-only or read-write with this particular team, or with just these team members with this specific role. So there's role-based access control even within a project in the platform. Now, I've mentioned many of these technologies already, but if you're using the Hopsworks feature store and you want to write data in, and also for reading data as well, you're able to use typical programming language frameworks such as Pandas, Python, Spark, even support for Scala Spark and Java Spark, not just PySpark. Spark Streaming, and Flink. If you prefer to keep your data in a data warehouse and compute features with SQL, that's also possible. You can take tables defined and we have many native connectors for Snowflake, Redshift, ADLS, GCS, S3, our own file system HopsFS, and JDBC, which covers many different databases. And you can perform the SQL for computing the features in these external data warehouses, which is often very efficient, and make the ready-made features available in our platform, where they can be joined together with other features that maybe didn't come from the data warehouse. Maybe they came from some Python program or some Spark program. So that's it. I've covered Hopsworks as a platform, and we've talked and drilled into detail on the performance and also the availability of feature stores. We looked at 4 different breakdowns of what performance and availability are. We have high availability, which is typically replication, and that relates to the feature store. We talked about latency. So latency typically relates to the online models that need to get low latency access to the features. Throughput covers writing to the feature store, reading for online models, but also reading for creating training data and batch scoring data. And then finally, we have the notion of freshness of features, which differentiate feature stores from traditional databases. Because you care about how fresh your features are, because it determines how performant your models will be in a given problem domain. So if your problem domain is operational and it needs very recent data to make really good predictions, you really want to get your feature freshness as good as possible, and that might mean streaming analytics engines to compute your features. So Hopsworks is a little bit more than a feature store. There's data science capabilities, it has compliance, governance, efficiency at scale, and it's an open source platform, and it's very modular. It'll plug into any data sources you have, any data warehouse, and even any model serving environment. That's it. Thanks for listening, and I hope you learned something more about performance and availability of feature stores.